Okay, thanks, Peter. Yeah, let me explain about the titles. Um, I sent Peter my title and abstract called Tales of Tail Dependence, and then received an email from Brian Rich and another one from Elizabeth Manshart, who said that my title was both precious. I think one described it as precious and the other as adorable, and so I needed to beef up the title, I suppose. So that's where the destruction, mayhem, and disaster comes from. So the goal of this talk, it's not really a research talk. Whoops. Okay. Um, the main part of the talk is um, is part A here, which is supposed to just talk about the ideas of tail dependence, how we describe dependence in the tail, how it's different than we usually describe things. And I'm going to give a mathematical framework for which I think is useful for describing tail dependence. Um, and it's perhaps not the only way it can be done, but there are both practical and theoretical reasons that it kind of makes sense. And it could get really math heavy there, but I'm going to try to not make it so. I'm going to try to give you enough intuition for what's going on and why we need to think about, or why this is a useful framework for talking about tail dependence. And I'll wrap up part A giving kind of essentially a toy problem, which is stolen right from a book, where we do kind of what's typically done in multivariate extremes, and you try to, I'm going to assess or estimate the probability of falling in some risk region. And then if there's time, I'll talk about some work that I and students and collaborators at NCAR have done using this framework within the general application area of atmospheric science. And we can, if we don't even get to part B, if there are enough questions in part A, that's fine. We'll do as much of part B as there's time for and interest. And well, anyway, so that's the plan for the talk. So just a couple of slides about kind of univariate extreme value methods. Let me see if I can use my pointer here. In most of statistics, what we often try to do is try to describe the bulk of the distribution. That's with means and variances and covariances to describe dependence, and it works really well for describing the bulk of the distribution. But when we get up here and we want to talk about the tail of the distribution, all those methods really don't apply. And so we have to have different methods for describing the tail. When we're dealing with just univariate data, there are pretty well-known methods, and pretty well-known not only in statistics, but even in atmospheric science. Say there are plenty of articles in the atmospheric science journals that are using extreme value methods, fitting Gev distributions or generalized Pareto distributions to describe the tail of the distribution. And so, as I kind of described, in univariate extremes, there are a couple of different models which have asymptotic justification for using them, the generalized extreme value or the generalized Pareto. These distributions are flexible models for the tails, and there are essentially three types of tail behavior that you can characterize. There are bounded tails where there's an upper limit which can't be exceeded, light tails where the tail of the distribution just decays exponentially, and then there are heavy tails where the decay is as a power function. And it's often in the heavy-tailed settings that extremes is most useful. Things like precipitation has a heavy tail, and we know that large precipitation events can be much, much larger than typical precipitation events. And so often interest when dealing with extremes is when your phenomena have a heavy tail. So we do something strange at first in extremes, at least it seems, in that when we're doing an extreme value analysis, we'll throw away most of the data and not use it at all. We'll retain 5% or 3%, or in some situations, especially in kind of financial applications, they'll use less than 1% of the data. And the reason for that, kind of heuristically, is that the extreme phenomena, what drives the extreme behavior can be something pretty much entirely different from what describes the day-to-day behavior. And so the idea is to let the tail speak for itself, throw away the bulk of the data, just use the data in which extreme behavior is happening, and then model only that. And then this last bullet point is going to be important for us too. The aim in an extreme value analysis is often to extrapolate further into the tail than your data reaches. You can imagine trying to estimate a 100-year event with only 40 years of data. This is commonly done. And so because these distributions are asymptotically justified, we have some justification for performing that extrapolation. As you can imagine, as you extrapolate further and further, the amount of uncertainty with your estimates, just think of your confidence intervals with that return level, get larger and larger, but nevertheless, we can get some sort of estimate and also convey some sort of measure of our confidence or our uncertainty associated with that estimate. So let's talk about multivariate extremes. Now we've got more than one variate, and what we want to do is we want to talk about the tail behavior, and so that's the joint tail with these two variates. And apologies to people who've seen me talk in the last couple of years. All of my talks essentially begin with this slide, and the reason for that is because I think these two data sets illustrate two very different tail behaviors. So the data set on the left is ground level ozone data. Actually, what's on the x-axis is ground level ozone as predicted by an atmospheric chemistry model. So this is prediction at some location, say tomorrow. And then on the y-axis are the actual observations at that location for the time that was predicted. And so you can see that this data is obviously dependent. When the model predicts that ozone is going to be higher than average, ozone tends to be higher than average. There's positive correlation with this data. But if you look at the extremes, you notice something interesting happening. Kind of out here where I'm putting the arrow, what's happening is the model is predicting very high ozone, extremely high ozone. These are the highest predictions that we have. But you notice that the observations actually don't correspond to the highest observations. And on the other hand, when we have the highest observed ozone, the model isn't predicting it. So in some sense, you can look at this data and you can say, okay, what's happening with this atmospheric chemistry model is that it's doing a pretty good job of predicting ozone in the bulk of the distribution, but it's missing the tail. So there's a question about log ozone, and I don't remember what the units are here, but essentially the model output and the monitor have been are on the same units, and that's all that's important for us, is that we're seeing essentially the scales of these guys are the same, and we're seeing the dependence as we move further and further and further out into the tail. It appears that it gets weaker and weaker. Now, the panel on the right is also ground level ozone, but this is observations, and this is for the x-axis is for Alexandria, Virginia. The y-axis is for Arlington, Virginia. So these are two locations that are pretty close in proximity. And these are just observations. So what we see is that when Alexandria is at its highest levels, Arlington tends to be. Now, that's not universally true, but we have strong probability of these two variates being large at the same time. And this data set, this one on the right, I choose to illustrate this behavior. And I want to let you know that this is actually the strongest, what I'm going to describe as tail dependence that I've seen in actual data. So we're going to look at this data for several slides, and keep in mind that the guy on the right is as strong as anything I've seen in my work in this area. Okay, so what we need are we need frameworks which can describe the difference between the tail dependence we see in the data on the left and the tail dependence we see in the data on the right. And so correlation, although the data on the right is more strongly correlated, I'm going to argue that correlation, because it essentially measures spread from center, it's not a good measure for dependence for extremes. So how do we, if correlations and covariances are out, how can we talk about tail dependence? And so there's an idea of asymptotic dependence and independence, which essentially was illustrated on that previous slide, which is a start to describing dependence in the tail. And it's a pretty easy concept to grasp. So we say that a random vector, xy with common marginals, and the common marginals is important, as you'll see in a minute, is asymptotically independent if the probability that x is big, given that y is big, goes to 0 as our definition of big gets bigger and bigger and bigger. So this x plus is just the right endpoint of the distribution. And so we're just saying as our threshold u gets larger and larger and larger, if y exceeds that threshold, the probability that x exceeds that threshold goes to 0. And the figure on the right, the figure on the left, where we have the modeled ozone versus the observed ozone, appeared to have asymptotic independence. And let's see. Now we have to have common marginals, because this definition, and at least the first definition, we have to have the same notion of big for both x and y. So if x and y don't have common marginals, you can still essentially describe asymptotic dependence and independence, but first you have to account for the marginals. So this definition below is just equivalent. You apply, if you know the marginals for x and y, you apply the CDF to them, you end up with uniforms, and so this definition is essentially equivalent. If this limit is greater than 0, then x and y are asymptotically dependent. And so this gives us a starting point for describing kind of the behavior we saw in that we described on the previous slide. And so to talk about tail dependence, at least using this framework, we need to at least have a common marginal or account for common marginals. And although this is a beginning, this doesn't give us the whole picture. And so we'll build from this idea. Okay, so there are many measures of dependence in the tails. Chi-bar is a pretty straightforward one. It's essentially an empirical measure of asymptotic dependence. And so these figures on the left and right correspond to those data sets that we looked at before. And what we see is that as I move further and further up for that left data set, as I move up to a higher and higher empirical quantile, that conditional probability seems to be drifting off towards 0. And so this figure implies that data appears to exhibit asymptotic independence. And the figure on the right shows that the data on the right, the Alexandria and Arlington data, appears to exhibit asymptotic dependence. We don't see that drifting off to zero. Of course, as we get higher and higher and higher, we've got less and less points to estimate with, and necessarily things get kind of flaky as we move further and further out. And so there's some art to interpreting this, but you kind of look at the behavior of this thing and you say, do I believe this is drifting off to zero or not? Now, what's important, in extremes, we're often really worried about the asymptotic dependence setting, because what that means is that your two variables can be large at the same time. And so you can imagine, well, we'll see an example here in a minute where I look at wave height and storm surge. And if wave height's big, or if storm surge is big, or if they're both big at the same time, then the water comes over my seawall. In finance, people are worried about losses with financial instrument 1 and 2. So we're often worried about the case where we have asymptotic dependence. And unfortunately, few of the models that we pull off the shelf exhibit asymptotic dependence. For instance, the Gaussian model, if you have anything less than perfect correlation, you fall into the asymptotic independent setting. And so remember that one of our goals is often to extrapolate further into the tail. If we fit a Gaussian model, think correlations to X and Y, and then we extrapolate further into the tail, well, we can be underestimating the probability of X and Y both being large at the same time, because the Gaussian model, as we move further and further into the tail, that dependence gets weaker and weaker and weaker. So we need models which exhibit asymptotic dependence. Okay. So let's look at a toy problem for tail dependence. And so this is kind of what has been done. Okay, I'm looking at Michael's question. Notion of asymptotic independence looks odd to me. Why not look at conditional over marginal greater than u, and then ask if that tends to 1? Okay, so Michael's question, I believe, is imagine that as u gets larger and larger, this limit goes to 1, and that would be an extremely strong type of tail dependence. And I believe that the only model where you could have that would be if you had complete dependence, exact dependence. That knowing X would let you know Y exactly. So my window says Michael is typing. I'm going to wait and see if he has a follow-up question. I'm by the margin. Michael, Peter, can you turn on Michael's mic? Michael, I'm not hearing you. Are you? Oh, okay. So I think what Michael's saying, let me see if I can try and answer that. Michael said, think about the conditional distribution. And of course, the conditional distribution is the probability that both x and y are bigger than u, divided by the probability that y is bigger than u. And if that's going to go to 1, then anytime that y is bigger than u, x also has to be bigger than u. And so I still believe, Michael, that that is only going to occur if we have perfect dependence. Am I not thinking about that correctly? Okay. Um, so I'll press ahead, and I guess a thing to keep in mind is that NC State just asked a question, and I'll get back to it here in just a second. But the thing to keep in mind is that asymptotic dependence, if there are lots of cases where, in fact, many probabilistic models fall in the asymptotic independent case. In fact, that's why I'm going to rely on this framework that I'm going to describe here in a little bit, because there aren't many models out there that exhibit asymptotic dependence. And if you look at a lot of data, there's an awful lot of data which appears to be asymptotic independent. But hopefully I've motivated that we could be very worried if we're in the asymptotic dependent setting. If we're in that asymptotic dependent setting and we fit an asymptotically independent model, then we are going to underestimate the probability of a jointly large event once we extrapolate further into the tail. Okay, so now let me look at NC State's question. The bivariate Gaussian is the simplest bivariate parametric model. If this one has asymptotic independence, what parametric model will give asymptotic dependence? And so, yeah, I'm gonna motivate that here shortly. I'm gonna give you a framework for talking about asymptotic dependence. And Brian's right. The bivariate T exhibits asymptotic dependence, and the bivariate T is going to fall in the class of distributions that I'm going to describe, these regular varying distributions. And the advantage of using this model that I'm going to describe, rather than just saying, let's fit a bivariate T to the whole data set, is that I'm going to, the regular variation framework is a framework which is only defined in the tail. And so we're going to do the usual extremes thing of throwing away the bulk of the distribution and using only data in the tail to model that, to model the dependence. Okay, so this is good. I think the question is working pretty well. Hopefully I'm answering them adequately. So, but please, if you have questions, feel free to chime in. As I said, we can spend the whole time on part A, just talking about these models for tail dependence. Okay, so here is a kind of a typical application. And as I said, this is stolen right from a book. This is stolen from Stuart Cole's book. What we have are data talking about wave height and storm surge from some location in England. I've created a risk region, and this is fabricated by me, but you can imagine that if wave height is high enough, our seawall, the water comes over our seawall. If storm surge is high enough, the water comes over our seawall. And if they're both large enough, then we flood. So our risk region is out here. And what I want to do if I'm in the insurance business is I want to assess what's the probability of landing in this risk region. Now this data appears to be asymptotically dependent. If I look at my chi-plot, I have less dependence than what I saw in the Alexandria and Arlington data, but it doesn't appear to be drifting off to zero. And so if we fit an asymptotic independent model to this, we'd likely underestimate the probability of landing in this risk region. We the variance, our wave height, is on a very different scale than storm surge. Notice this is running from 0 to 15. Storm surge is running from actually below 0 to 1.5. And so what I'm going to need to do is I'm going to need to account for the marginal behavior to describe the tail dependence. And I'm not going to be able to do this, although this chi-plot tells me, hey, we're in the asymptotic dependent setting, it doesn't provide me a model for assessing the probability of landing out here. So I need more than just that summary measure. Okay, so here's where things get mathy, and don't panic. So there's a framework called multivariate regular variation, and there's theoretical justification for this framework. It has direct ties to the class of multivariate extreme value distributions. But for our purposes, we're going to look at this as just a general model for the tail, and its very definition only describes tail behavior. And so we say that a random vector z is regular varying if there's a normalizing sequence Bn such, and the normalizing sequence is given here. But if you normalize z by Bn and take the probability that the normalized guy is in some set dot, as n grows, that probability is necessarily going to shrink. If we balance that probability out with n, if we obtain convergence, then we're in this regular variation setting. Now, what this means, regular variation essentially means we have a heavy tail. And so Brian's comment about the bivariate t, if you have a t distribution with a heavy tail, hey, this is why you're in this regular varying setting. Now, what's magical about this is that there's, you can show that this scaling property down here holds, which says the measure of, if I know the measure of a set B, and I want to know the measure of a related set T times B, so this just projects the set B in some with some scale T, I know that measure. And so what this scaling measure does is it's going to allow us to extrapolate further into the tail. In a picture, all that scaling property says is if I know the measure of this set B, then I know the measure of this set TB. Okay, so we can see, okay, now we can kind of see how this is going to allow us to extrapolate. This nu is a measure, it's not a probability measure, and it's essentially, if you're familiar with point process literature, you can think of this as the intensity measure of a set. What this scaling property implies that Cartesian coordinates aren't going to be nice. Instead, the way things scale, polar coordinates are going to be useful for us. And so, so here is an equivalent definition. And it says, take your random vector, take its magnitude, call that the radial component, take its direction, call that the angular component, which I'm calling W. Then z is regular varying if there exists this normalizing sequence such that you obtain this convergence, which is shown there. And what's important is that over here on the right-hand side, what we converge to is a product measure. The first guy is this r to the negative alpha, and that shows that we're in the heavy-tailed case because our probability is decaying like a power function, or our measure is decaying like a power function with the radial component. The H of A talks about the distribution of the angular components. And it says that as n grows, these guys become independent. And so what I can do is I can model the radial component and the angular component separately. And so again, all this essentially says is the left-hand side says as points get big, The right-hand side says radial and angular components become independent. Um, and so this angular measure h is going to be critical to us because it describes the distribution of the directions that we shoot. So, um, so in summary, what we have is a general framework for heavy-tailed multivariate distributions. But our framework only talks about the tail because the left-hand side just says, as points get big, here's our behavior. And so pictorially, here's what's going on. So think of points kind of lying way out here, away from the origin. Those points, if we're in this regular variation framework, the distribution of those points is described by a radial component, which just measures the distance from the origin, and an angular component, which lives down here on the unit ball, because the directions of the vector are, of course, all of unit length. You can use any norm that you want, and there's some mathematical convenience in a certain situation to use the L1 norm, so that's why I have this funny shaped unit ball. This is just the set of points whose L1 norm is 1. But there's a distribution that lives down here, and that describes the probability. With that, we can obtain the probability of firing in different directions. If that distribution has a bunch of mass right here in the middle, what that means is for large points, well, they're going to be large in all components because all components essentially have the same magnitude to end up with an angular component that's here in the center. If our mass is toward the edges or the corners, what that means is large points, if I have a bunch of mass at this corner, I'm likely to have a large point where the angular component is essentially just in the direction of z2. Okay, so what this gives us is a framework for modeling the tail. Our definition, our framework only exists in the tail, and so we're going to do the usual extremes thing of throwing away most of the data and only retaining a small subset to describe the tail behavior. And there's a problem, though, in that this framework requires us to be in the heavy-tailed setting, and we might not be. In fact, my wave and surge data isn't heavy-tailed. So what I'm going to do when it comes to statistical modeling is I'm going to take my marginal distributions, estimate them. I'm going to transform them to something nice, which in my case is going to be something heavy-tailed. And then I'm going to describe the dependence of this data after the marginal transformation. And that might sound really familiar to you because this is what copula people do. Copula people will take their data, transform the marginals to be uniform 0, 1s, and then fit their copula model of choice to that data. This is similar, but there are a couple of important differences. One, this framework for this regular variation framework allows us to have tail dependence. Most copula models, if you look through the Nelson book, and that he's got a long catalog of copula models, very few of those copula models exhibit tail dependence, and the ones that do essentially were derived from extreme value models. Second, a big difference between this setting and the copula world is most copula applications take all of the data and try to fit a model to all of the data. Here, what we're going to do is we're going to throw away most of the data, retain only a small bit of it, and only model that. But I am going to need to go through this marginal transformation so that my data, which lives in the real world, fits nicely with this probabilistic framework, regular variation, which lives happily in probability land. Okay, so what I'm going to do is I'm going to switch my marginal so that I'm in a really, really heavy-tailed case. The alpha, which appeared in my previous definitions, which describes my rate of decay, is going to be 1. So this means that things are really heavy-tailed. And after that marginal transformation, the radial behavior is known, so all I have to do statistically after the marginal transformation is model the angular measure. So what I have here is, this goes back to our very first slides. The slide on the left is the model versus observed ground level ozone. The one on the right is the Alexandria and Arlington data. But what I've done now is I've transformed it to this very heavy-tailed marginal transformation. When you look at these scatter plots, the first thing you should ask yourself is, where'd all the points go? Well, what's happened is, because we've transformed to something that's so heavy-tailed, the points have all converged, most of the points have all converged to the origin. And because we've transformed to this heavy-tailed distribution, all we essentially see are the really big points. And that's, of course, all that we're concerned with anyway. What we can see after this marginal transformation is that the behavior of those really large points is very different for the left plot and the right plot. The left plot, all of the mass is essentially on the axes, and that's because when the model was saying ozone's going to be really high tomorrow, well, we observed ozone to be something, but it never was really, really high, and anything that isn't really, really high essentially collapses down here to the origin. And so we end up with mass along this axis, and from a similar argument, we end up with mass along the y-axis. The figure on the right has points out here in the interior. And so what that's saying is, oh yeah, the ozone in Alexandria and Arlington can be large at the same time. Now, you might look at this plot and say, it doesn't look like they're that strongly dependent. And what you have to do is throw away all of your pre-learned intuition about talking about scatter plots, because we're used to thinking of correlations, covariances, elliptical shaped clouds. And of course, if you had a cloud that looked like this, you'd say, gosh, that doesn't look like there's much there's much dependence here at all. Actually, the converse is quite true. After this transformation to something heavy-tailed, remember, this is the example that exhibits the most tail dependence of anything that I've come across. And so what this means is that there's points here in the interior implies that we've got very strong tail dependence. The plots on the bottom are empirical estimates of the angular measure. So think of drawing the unit ball down here. I'm sorry, I'm using my cursor, which doesn't work. Think of drawing the unit ball down here near the origin, and then just taking the largest points. Think of the largest 3 or 4%. I think I used 3% for these data. This data. Largest is largest in terms of the radial components. So what I do for all those largest points is I map their direction back to the angular measure, and here's an estimate of that h, the distribution of angles. And in the asymptotic independent setting, what happens is that h converges to mass just at the ends of that unit ball. You have mass at the edges and nothing in the middle. When you have asymptotic dependence, you end up with mass in the middle. And again, we have to retrain the way we think about histograms. But this histogram, because it's essentially flat, implies, hey, wait, we've got a really strong level of tail dependence. So if you're sitting here thinking, wow, things are really different here, that's on purpose. The way we're describing dependence in the tail is very different than we're used to, but hopefully you're seeing that we have a construction which allows us to really focus on what's going on in the tail. So what do we do with that? Well, let's go back to our toy problem. On the left is the transformed data. So remember what the original plot looked like for the wave and surge data. We had that risk region, which kind of was a line. It wasn't at 45 degrees, but that slanted line down there. What I have here on the left is now the transformed data. After I take that data, estimate its marginals, convert them to something nice in regular variation world. The data looks like this. We have some points in the interior, meaning that we've got some asymptotic dependence. The large points seem to be a little bit closer to the axes than in the previous example, and that indicates that the level of dependence for this data is less than in the previous data. This dashed line is the risk region in this transformed space. And so what I want to do is I want to find the measure of this set A star, because the measure of that set, I can then work backwards through my definition of regular variation, and I can end up with an estimate of the probability of landing in that set. So to get an estimate of this A star, what I need to do is I need to estimate my angular measure, and so that's what I'm trying to illustrate here on the right. These are the large points. Essentially, they're the top, I think the top, okay, it says right here, 0.95 empirical quantile. So I'm taking the top 5% of the data in terms of these radial components after transformation. I've zoomed in. Notice that the axes here go from 0 to 500. So it's essentially this small box here. And these rays that are extending out are just pointing to points that lie outside of this zoomed in picture. So what I need to do is for all of these large points in red, I need to map their direction and estimate the angular measure. So I can do that. Here's the histogram of that. There is quite a bit of mass on the axes, but there's also quite a bit of mass here in the interior, which says, okay, there is the possibility that these guys can be large at the same time. And it looks like, okay, I'm having a little trouble on my screen here, but what I'm going to do is I'm going to fit a parametric model to this angular measure. And so if you're seeing the h of w equals stuff, this is a parametric model for my angular measure. Okay, I've got a question from NC State. Is the angle in the histogram between 0 and 90 degrees? Yeah, you can think of it that way. I've got, I'm using this L1 norm, and so thinking of things in terms of degrees or radians isn't so nice, but you can essentially think of this as being 0 degrees and 90 degrees for the direction. And then the second question is, for high dependence, wouldn't we want concentration around 45 degrees? And the answer is yes. If we had perfect dependence, what would happen is that the points would end up lying right along the 45-degree line. So I've gone back a couple of slides, and I'm looking again at the ozone data for Alexandria and Arlington. In practice, that never happens. And because we've transformed to something that's so heavy-tailed, essentially there's these huge jumps between, there's these huge spacings in the largest order statistics. And so remember that this actually is as strong, this picture on the right is as strong as strong of tail dependence as I've seen in any actual data setting. So although although your intuition is right that very strong dependence, essentially perfect dependence, would imply that you'd have a concentration around 45 degrees, you never see that in practice. Nevertheless, we do have strong tail dependence here, and we need to account for that when we're estimating the probability, if we were estimating a probability of a risk region for this, and we need to do it again even in the next slide, where the the asymptotic dependence isn't strong, but as you're going to see that if we neglect that asymptotic dependence, we're going to get a silly estimate for the probability. Okay, so your question is good. It indicates you're following what the general gist of things here. So, okay, so here is an empirical measure of the angular measure for the wave and surge data. I fit a parametric model, which is this H of W. This is essentially the density of that model. I estimate beta via maximum likelihood. I get a beta of 0.68. That 0.68 value isn't all that interpretable. In fact, it's reversed of the way you think of correlation. Higher values imply less dependence, but 0.68 is certainly a non-negligible amount of tail dependence. We've got tail dependence that we need to account for. Once we have this, essentially all you have to do is integrate to find the measure of this set, which I'm again using my cursor, which you don't see. I need to integrate to find the measure of this set here. And you can do that, and then you can work backward from our definition of tail dependence, and what I get is that there is a 0.00158 probability of any day exceeding this risk region. And I can get a confidence interval of 0.00147 to 0.00170. Now, that probability is actually pretty large because this is for any given day. And I picked a risk region in this example that wasn't all that extreme. Notice that we have two observations that actually fell in this risk region, and that's often not the case. Oftentimes, you need to extrapolate beyond the range of the data. Your risk region might be way out here where you don't have any points observed. But the reason I chose this not so extreme risk region is so that we could compare our estimate with an empirical estimate. So, oh, and I guess I deleted those slides. But it turns out that our estimate is a bit higher than the empirical estimate. And the uncertainty associated with the empirical estimate is quite a bit larger because essentially when you're doing the empirical estimate, you're not using any information other than does this point exceed fall in the risk region or not, and you're really using very little information about the points down here. What we're trying to do in extremes is use some information about the points near the risk region to model to essentially model our angular measure, and then we can use that to extrapolate out. Okay? So now we get to part B, and I realize that we're 50 minutes in. So let me pause here. It looks like somebody's typing a question, and actually let me jump way ahead here while the question's being typed. Okay, I thought I had a summary slide, but it looks like my summary slide is just talking about the applications. What are the takeaway messages of this talk thus far? The takeaway messages, I wish I'd had my summary slide. Takeaway message one is when we do extreme value things, we want the tail to speak for itself. We throw away the bulk of the data. We retain a small subset of the data to talk about the extremes. And more disciplines are becoming familiar with this idea. Atmospheric science is doing a pretty good job of doing univariate extremes and fitting GEVs and GPDs. And I think that they recognize that you can be misled if you about the tail if you try to fit a model to the entire distribution. What I've tried to illustrate here is that there are frameworks for doing that in the multivariate setting. And one of the things that we need to be concerned with is this case of asymptotic dependence, because if we're in an asymptotic dependence setting and we fit most of our familiar models, which don't exhibit asymptotic dependence, then we're going to underestimate the joint probability. And unfortunately, I deleted the slide where I did that empirical, I did the comparison. But the probability that you estimate if you assumed asymptotic independence essentially is an order of magnitude lower. And so we would way underestimate that probability if we don't account for asymptotic dependence in a sensible way. And what we do in part B is, I think we've done some kind of cool work which extends the ideas of this framework to settings that aren't just descriptive anymore. Most of the work done in extremes is very descriptive. Essentially, it's like the toy problem that I showed, where you're saying, what's the probability of landing in this risk region, or what does the 100-year event look like? And some of the cool work that some students have done recently is trying to use this framework not only to describe extreme behavior, but to understand what drives the extreme behavior. And I think that's an area of extremes that is just starting to be explored. So let me say, Air Worldwide says, can you say anything about the sensitivity to the transforms you use, the model you use for the angular measure, or the number of data points you retain? Yes, there is. There's been a lot of work on, well, kind of a lot of descriptive work talking about the sensitivity to the transforms, and it's quite sensitive to the transforms. That's something which I think what one should do, and what I didn't do in this toy problem, is to accurately propagate the uncertainty of the marginal distributions through, so that you end up, the uncertainty that I reported when I gave you the confidence intervals really only talked about the uncertainty after the marginal transformation. And a more honest accounting of the uncertainty would also talk about the transformation of the marginals, which I didn't spend much time talking about either. But it is fairly sensitive to the transforms one uses. And nobody that I've seen has a good answer for addressing that sensitivity, but the best way to do that would be, or at least we can try to describe the uncertainty associated with that. The model I used for the angular measure was a very simple parametric model. When you're talking about the angular measure of something that's two-dimensional, that becomes one dimension, and there are plenty of models out there. There are some that are more flexible than not. One of the present challenges of multivariate extremes is coming up with sensible models in higher dimensions. And there are some models out there that do an increasingly better job, but as author of one of those models, I'll tell you, there are deficiencies with those. One could make a fortune if you came up with a very high dimensional multivariate model. You could sell it to Goldman Sachs and make a lot of money. I haven't done that yet. Number of data points you retain, there are some diagnostics. Essentially, the number of data points you want to retain is the number of data points where this extreme value framework is a good approximation to what you're seeing in the tail. If you're familiar with fitting a generalized Pareto distribution to threshold exceedances, there are some diagnostics which essentially say, above what threshold does the tail start to behave like a generalized Pareto? There are similar things in the multivariate setting, which says, essentially what it says is, above what threshold do the radial components and the angular components behave independently? So hopefully that answers the Air Worldwide question. Michael says, lost my sound there. What I was trying to say is that a different measure of asymptotic independence might be, oh, that the, so you're, um, Michael, it looks like you're taking the conditional probability and dividing by the marginal probability that x is greater than u. So if x and y are both have common marginals, then the probability that x is greater than u is the same that the probability y is greater than u, and essentially that expression is going to be the joint probability divided by the probability squared, and that gosh, the I think I'd have to think about this a little bit more. It looks like Michael's typing now. The if they were exactly independent with the same marginal, this equals 1. Okay, right. The if you go back to the regular variation definition, the bn that we divide by is regular varying of essentially inverse order of the regular variation of z. And essentially to get the right, to obtain convergence, if you start off with something that's regular varying, to obtain convergence, of course, you have to choose a bn which is growing at the right rate. And actually, an easy way to do that, and it's kind of essentially implied right here by the description of the normalizing sequence, is you dividing by the probability that the marginal is big is going to give you a right normalization. And so if you go back to the definition of chi, although x and y I haven't specified that they're regular varying in this definition, if they are, then you can look at this definition of chi really in terms of this regular variation framework. You have this joint behavior on the top and this marginal behavior of the probability y being greater than u is your normalizing guy, and you're going to obtain convergence to a limiting measure. And so I think for kind of those reasons, it's really, I kind of presented it in reverse order, but this framework of asymptotic dependence and independence, if you start with regular variation and move forward to this idea, there's a really nice relationship there as well, which would be lost if you were normalizing by the square. You wouldn't converge to a limiting measure. Peter Craigmale, any relationship to Heffernan and Tong? Yes, and I still haven't figured it out. The one of the so I spent a whole lot of time talking about tail dependence. And one of the questions is, what do you do? Okay, if you've got data that are asymptotically independent, what's the right thing to do? Should you just fit a Gaussian model? I would argue no, because a Gaussian model doesn't necessarily focus on the tail. It just is, it's a model which exhibits asymptotic independence, but you could still be doing the wrong thing in the asymptotic independence. So there's an awful lot of work in extremes going on right now to describe tail dependence in the asymptotic independence setting. And a student of mine and I have a recent paper which talks about that. And the Heffernan and Ton model also talks about asymptotic independence. And it's really a funny setting for this. The best reference for the Heffernan and Ton to relate the Heffernan and Ton stuff to the regular variation stuff is a paper by Heffernan and Resnick. Resnick really is where I stole all of this regular variation stuff from. And Heffernan, of course, is the lead author on that Heffernan and Ton paper. And essentially, Sid contacted Janet and John, Janet Heffernan and John Ton, and said, hey, let's sit down and try to reconcile these things. And they tried to, but the Heffernan and Ton thing is still its strongest argument for theoretical justification is that there are a whole bunch of models that fit into their framework, but there isn't really a unifying framework underlying their approach.
Okay, so we're at 12:05, I guess. You've been talking quite a bit. Do you want to say a little bit about Part B, or I'll let you decide?
There are great papers out there about this. Let me just say, let me just give you a flavor of what we did in one slide. Well, okay, 2 slides. Essentially, what we tried to do was we tried to ask if there's a phenomenon called the Pineapple Express, which creates extreme precipitation and flooding on the Pacific coast in the winter. And we wanted to use this multivariate framework to answer the question of, are regional climate models able to capture the Pineapple Express phenomenon? And so what we did was we built essentially a bivariate model for between reanalysis driven climate models and observed precipitation. And the importance of reanalysis driven is that the regional climate models weather for any particular day should resemble, in some sense, what's observed on the ground for that particular day. And so we truly have bivariate data here. And essentially what we were asking is, are these two things, is the climate model tail dependent to the observed precipitation? And we found, in fact, that it was, which actually says that the climate model is doing something remarkably well. When we actually observe precipitation to be at its largest, the climate model tends to produce its largest precipitation. And so in that sense, the climate model was getting the Pineapple Express right. Now, the numbers that came out of the climate model were completely wrong. You'd have to do some sort of downscaling to take the numbers that come out of the climate model and translate them to something that you'd see on the ground. But in this tail dependence setting, again, the climate model produced its most extreme precipitation when we saw its observations. And so I think that was a pretty powerful statement for this regional climate model, saying, well, at least for this one phenomenon, it got it right. We looked at summertime precipitation in the Midwest, and it got it completely wrong. And that's not a surprise, because summertime precipitation in the Midwest is local and convective, and it's not surprising that the regional climate model didn't produce its most extreme behavior when we were seeing it on the ground. So that's one example of looking at tail dependence and not using it to describe a risk region. We were really trying to understand the relationship between observations and climate models.
Thank you. Do we have any more questions for Dan?
All right, Suze, you'll have to tell me if I was able to. Suze sent me a message ahead of time that said, is this going to be understandable to us? And so hopefully it was. If you got the message that we need to describe dependence in the tail differently than you're used to, that's a start.